Welcome to KF 5008, Program Design Development, lecture for the week 3. This is the algorithm side. This week we're sorting out. A lot of people say, why do I need to learn about sorting? It just sounds so mundane and so boring. But let me tell you about this. I was taught to sort by a nurse in King's Cross, and she told me that every hospital has a filing cabinet. A big metal cabinet that everybody in the building prays they never have to open the doors of. You see, inside the filing cabinet are triage cards. Triage cards are brought out when there is a major emergency, when the hospital is overloaded with new cases. So there could be a major disaster, a major explosion, a train being derailed or whatever, and the hospital becomes overloaded with people. So imagine you're in the middle of a large disaster. And what they do at that point is they go into what they call triage. Now, as a quick tangent, triage has 3 major modes. The first one is minor, and this is people who are going to recover. They're the green ones. And then you have the people who are likely to die. Now, typically, if it was a normal disaster, a normal emergency, and you were going to a normal AR, emergency room, then the doctors would be trying their best to make sure that that person survived. And even though the odds were slim, they would still go all the way out, even though they know they were probably going to fail. However, in a major disaster, they're given a black card. They don't know this yet. And that card basically means they're given morphine, they're given as much pain medication as they like, they're made as comfortable as possible, but they will probably die. And then finally, there's the red group. They're the intermediate. Now, those are people who, if there is some medical intervention in the near future, they will probably survive. And if they don't get that medical intervention, they will probably die, but they have a good chance of survival with intervention. And those are the people that they concentrate on. Now, of course, people's conditions aren't fixed. They go up and down all the time. Blood pressure may go up, bleeding may start, lots of different things can happen. So what they do is they have a series of cards that they can wipe out. So they have little kind of spaces they can write on. And what they do is they have a card attached to the patient with a patient number on it. And that patient card is then, there's a duplicate of it on a table somewhere. And that's typically run by the triage nurse. Now, the triage nurse's job is to keep those cards in order. Now, that means those, a doctor may come along, pick one of the cards up for patient 28, and he may say, actually, this has gone from a level 6 to a level 12, so you want to resort the cards. And the thing is, the triage nurse has to keep the cards sorted at all times. And there could be a lot of cards. It could be like hundreds of cards. Or in the case of a major tropical disaster, it could be thousands of cards. Yeah. And she or he, typically is a she, let's face it, she or he has to keep those cards sorted at all times. So if a doctor at any point says next patient, she knows exactly who's at the top of the queue to get treated next. And if she fails to keep those cards sorted, if she makes a mistake, then someone could die. Now, typically at this point, we do a demo, and I challenge one of the students to actually try sorting cards quicker than I am. And I'd like to believe that I actually win those contests more than I lose. I typically do. And the only time I lose is when they're actually using the particular magic algorithm I was taught by this nurse. So, why not sit down for a second and see if you can find something you can sort, a pack of cards, or it doesn't really matter what it is, but try and sort them into order and then make them random again and sort them again and try and figure out how you would do that as quickly and efficiently and accurately as possible. While you're doing that, I'm going to talk about sorting, because sorting has been around for ages. The earliest tabulating machines, which were the earliest kind of paper computers built, were built for the American census. And one of the things they could do there was sort and filter particular cards out for the census. But to be honest, these days, sorting is everywhere. Every time you look something up in Google, sorting is going on. If you look at a website, again, if you're buying something, sorting is going on by the machine. Every time you look at something, it will be sorting. Okay. Even if you're not looking and buying, even if you're just looking at a web page on Blackboard, that's being sorted. I constantly get a list every time I look at the number of students. And even on your mobile phones, it's constantly sorting out which is the strongest signal and then using that as its in connection to the internet. So every second of every day, sorting is happening huge amounts. But how? Now, one of the things we're doing the sorting for is we're actually going to learn a lot about using the O notation that we learnt last week to understand how to choose an algorithm. So let's start off with the brute force technique. Remember what I said to begin with? Never underestimate brute force. Now, what's the simplest algorithm you could probably sit down and write out to explain to a machine how to do it? So let's imagine you've got a bunch of books and you're trying to sort them by height. And these are by height and by letter. And I just wanted to use that to show that you don't have to sort numbers. You can sort letters, you can sort heights, anything that you want to sort. As long as you can say one thing is bigger than another, then you can get away with it. So what have we got here? So this is bubble sort. How does bubble sort work? What it does is it picks pairs, an item and the item next to it. If the item next to it is unsorted, i.e. it's smaller, the second item is smaller than the first, it swaps them round. And then when it gets to the far end, it goes back to the beginning and starts swapping all over again. And you keep going round methodically, swapping and swapping and swapping and swapping and swapping. So here we go, it's nearly done. And you can see that the way that E is moving slowly upwards. Notice it's flashing every time it finds a non-swap. And you notice how E is slowly moving to its correct position. There we go. But it has to keep going until it reaches the end. And if it goes through the loop with no swapping whatsoever, then it's sorted. So how efficient is that? Why not sit down for a second and see what you think what your intuition for the O notation is. Here's some code to help you guess. So, can you guess the O notation for this bubble swap code? If you have available, write it in the notes and then stop the video, write it in the notes and then come back. Welcome back. Let's have a look. So, we can see in the middle of the for loop, this is the loop that runs up the array, and basically every time it finds a pair of items that are unsorted, it swaps them around. So if we double the size of the array, it's going to take twice as long. If we quadruple the size of the array, it's going to take 4 times as long. So basically, the time taken is proportional to the number of items in it. So it's proportional to n. But notice that loop is inside a bigger loop, and that loop basically will keep on going until the entire array is sorted. And there's a number of ways of computing that thing. It could be infinity, but in fact it will never go around more than the length of the array. So the worst case is you're going to go around n times, and then if the array doubles inside, it's going to go around another n times. So we've got 2 nested n's. Now remember, if your loops are nested, or if one O notation is nested in with another, you multiply them together. So this gives us an O notation of O times N times O times N, which is equivalent of O of N squared. What does that mean? It basically means if you double the size of the list, it will take approximately 4 times as longer to process. If you make it 3 times longer, 3 times bigger, it will probably take 9 times the amount of time. So that's how fast that method is. Can we do any better? It turns out in the history of computing and the history of sorting particularly, there is 1 and 2 fascinating figures. The first of which is John von Neumann. John von Neumann was the smartest guy in the room. And I don't really care which room you're talking about. John von Neumann was a Polish mathematician. By the way, when he studied his degree in mathematics, he also studied a degree in engineering at the same time. His dad wanted him to study engineering. He quite fancied doing mathematics, so he did both degrees simultaneously. He goes on, gets a PhD, leaves. It's in the height of kind of the entry to the Second World War. So being Polish, he flees. Being Polish, he flees to America, and he kind of hooks up with the elite of Princeton at that point, the kind of ultra smart American hipsters. Now, there's an interesting story about John von Neumann, which is basically at that point, if you were an academic in Princeton, you had a row of books, and most of them had fairly similar books, to be honest. They'd all read the same kind of books. And his party trick was someone would point at one of the books, and then they'd take the book off the shelf, and then they would flick to a random page, and he would tell them what the first word on that page was. And that's because John von Neumann had an eidetic memory, a photographic memory. He remembered everything he'd read. And it's one of the things that made him to kind of able to power through writing so many groundbreaking bits of works. You probably know him from the von Neumann architecture, and he was very fundamental in the early circles of computing, including, in this point, merge sort. Of course, my favourite story about John von Neumann is how he died. You see, John von Neumann wasn't tied up just with the early encryption, early computers. He was also tied up with the Manhattan Project, the making of the first atomic bomb. He knew so much about the American secrecy that towards the end of his life, he was dying of cancer. So what they did was they took him away from his family and they locked him up into a secret base in Nevada. And there he was surrounded by only the most trustworthy orderlies. And these orderlies were sort of sworn to secrecy because the American government was paranoid that at some point he might let out one of these secrets to one of the members of family, and then some Russian spy might find out. And one of the secrets they were defending was merge sort. So before we get heavily into merge sort, let's just have a quick tangent on merging. What do I mean by merging? Merging is a bit like a zip. You're taking two lines of items, yeah? And typically these lines of items are pre-sorted. So you've got two sorted lists and you want to merge them into one big sorted list. Now, how long would this take to do? Well, let's try and figure this out. Let's start off by understanding how it works. So what we do is we have two, what I'm going to call pointers, and these are just indexes into an array. And I'm using an array of integers at this point. It doesn't really matter. I could have anything that I can compare. Letters, numbers, strings, genomes, don't care. And what we do is we look at the first pointer, head A, the blue one, and we look at top B, that's the top of the B list, and we decide which is the smaller. So in this case, it's going to be item number 1. So we take item number 1 and we put it into lead C, and then we move head A forwards 1. So there we go. Head A has now become 3. Lead C has moved to the second item. Top B still points towards the first item in that array, which is 2 in this case. And then we do the same thing. So what happens here is, what's smaller, 2 or 3? I think 2. Let's move forwards. Now, what's smaller, 3 or 4? 3, obviously. So we move lead forwards, we put 3 in there, and we move head forwards. So the one that's been used up, we move forwards. The one that hasn't been moved up, we just leave where it is. So there we go, 5 and 40. So it's going to be 40, 5 and 55 and 58, and so on. We keep going until we reach the end. Now, how long is that going to take us? Let's have a look at the code. So remember from last week, how do we figure out what the order is just by eyeballing some code? Well, we count the number of loops. And as you can see here, we have one loop, and it's not calling anything. It's just doing a particular job with the array. So on average, if we double the length of the arrays, and one array is going to be longer than the other one, so if we double the length of the arrays, it's going to take twice as long to do. So merge is O of n. So if you have two sorted arrays and we want to merge them, it will only take O of n time. Now, does that inspire you to do a new form of sorting? Probably not, but hey, it was worth asking a question anyway. So let's have a look at this version. So imagine we take a list of items. Well, we can't merge that because it's just a single list, isn't it? So how about we cut that list into two lists? It's like, okay. Now we've got two lists we can merge together if only they were sorted. Well, perhaps we could cut those lists up into smaller lists and smaller lists and smaller lists and smaller lists until we get down to a list of one. Now remember, this is just like the way that you intuited when you played the guessing game. When you played the guessing game, you realised that if you cut your range in half, you do half the amount of work each time. And by cutting and cutting and cutting, you end up only doing a log of the number of operations. So let's see that in action. So we split into two groups. Each group we split into two groups. We keep splitting until we end up with an array of length 1. Now an array of length 1 must be sorted. So then we can merge those groups together. So here we see F being merged into that second group. Here we see A and C being merged into a group. There we go. And then we see those groups being merged together. And then we see the upper half being divided into single items and then merged together from one item to two items to three items and so on. And here we go. And they all come back. Now, the big question becomes, what is the O notation for that? So let's have a look. Let's have a look at the code. Now, I'm going to arm wave over the merge algorithm. We saw that a moment ago in the previous slides. You can always go back to look at that. And let's have a look at this. We've got the merge sort, and we're saying if start is less than n, midpoint is the middle of 2. That's exactly what you did when you did the guessing game algorithm. You guessed the midpoint, you split them in two. In this case, we copy them into two separate arrays, and then we start processing each separate array. And then we call the array again. Now, this is a way of going around a loop effectively. And it might make a bit more sense if we actually kind of have an overview of what's happening. So here we go. We start off with this array, 38, 27, 43, 3, 9, 82, 10. And we divide that into two. So there we get these two subarrays on the next level. We divide those again into two subarrays until we end up at that middle stage where we have those items. Now, then we go through the process of joining them together but merging each time. So 9 and 87 get merged, 10 gets merged to itself, 43 gets merged with 3 and 4, and so on. And then eventually we end up with the sorted version. So how many steps are we going through here? Well, if we double the length of this array, that would only add one layer here and one layer there. So it would just like add one effectively to the list of things to do. Let's have a look at this. So just looking at how many times merge is called, if we double the size of the array, it only adds one extra layer to another extra step to the splitting the merge sort algorithm. So this is an example of recursion. So before we get into doing this heavily, I want to basically just briefly mention the concept of recursion because it is a big, sexy idea in algorithms and in computing in general. And the thing is, if you don't really understand recursion, just go and watch the film Inception. It really just explains it all to you. Okay, this is a metaphor, you understand. I don't want to spoil the plot of Inception, but it all basically happens where these secret brain hackers have this thing that will break into your dreams while you're sleeping. So they steal onto a plane when a guy is going to be sleeping on a flight. And what happens is, in the dream, they meet up with the bloke in his dreams. But they have this brilliant hack, which means that they will then break into his dreams in the dream. So the idea is, in his dream world, he falls asleep and everybody follows him into his dream world. Inside that dream world, he's in a hotel. And again, the people in the dream world get him to fall asleep inside the dream world. So he ends up attacking this mountain fortress. And then the main character then slips into another dream world. So he falls asleep into that dream world, and he falls asleep into this world where this is huge kind of post-disaster apocalypse. And in order to get escape from everything, he has to escape from the dream world, escape from the snow world, wake up from the hotel world, wake up from the truck falling off the end of the pier world, and finally wake up in the plane. So that's how recursion works. And technically what we do is, so this is kind of how we'd implement it, the whole thing. So we have this method called fall asleep, and it has a depth. And then what happens is we basically say, if the depth is greater than 5, wake up. If not, run around doing stuff, we don't care, and then fall asleep, okay? And then we wake up. When that fall asleep has finished, we wake up again. And you notice you're running around from the green to the pink several times. So all we really need to do is to start off with a piece of code that will call that initial piece of recursion, and it will effectively move around in a loop. Now, our loop depends upon the log of the size of the system. So this comes back to the basic question: what is the order of the system? The merge sort is called log of n times, but it calls merge inside itself, which is O of n. So what does that mean? So because of the recursion, we're getting O of log of n, and we've got inside that we've got a merge of O of n. So if one order is called within another, so if it's inside the loop or it's called by another function, we then multiply them together. So we end up with O of n times O of log n, okay? And I don't want to go into GCSE maths, but we're basically saying it's going to be roughly proportional to the size of n and the log of multiplied by the size of log n. So is this good or bad? Do you remember our first algorithm, the bubble sort? It was O of n squared, and now we've got log n. So let's have a look at our league table. So O of n squared, well, that was a serious algorithm. That was kind of going to be time consuming. It was a polynomial algorithm. But now, if we look at log of n log n, it's not bad. So n log n is much faster than O of n. The curve, there's going to be a gap into those two sorts. So, just to summarize, merge sort. It splits the problem up. The merging itself, the taking of two lists and merging together, which are sorted, is O of n. We did that in a separate section. The splitting is O of log n, and because one is called by the other and the merging is called by the log of n, we multiply them together, which needs O of n log n. Now, the downside of this algorithm is it does need extra space to copy bits into. So who can we get to be smarter than the smartest guy in the room? Let's have a look. Let's move back to the 1950s. Tony Hall was not the smartest guy in the room. He was a PhD student who happened to be able to speak Russian. He was a linguist, not a mathematician. And he was in Berlin in the 1950s working on a machine-to-machine translator. Now, at that point, the Allies had people that spoke Russian, but typically they spoke Russian because they were Russian, and that meant that you were never 100% sure that they weren't actually a spy in your organization. So the British and the Americans had this big plan to make a machine that could translate, and also they couldn't recruit enough German-speaking, Russian-speaking translators to work for them. It also leads to one of my favorite stories. What they did was they would feed the machine English and then translate it into Russian, and then they would take the Russian and then retranslate the Russian back into English to see if it was working. And there was a famous case of the machine that took the words out of sight, out of mind, and it translated it into Russian and back out into English as blind and mad. So as part of this process, our researcher needed to sort words on a tape. He needed to sort the words alphabetically. But he didn't. He only had a cheap computer. He had no extra space to copy to. So he created the following algorithm. So what I like about this algorithm is it starts off just by going, just guess. And that's the really powerful part of this idea. It just begins by guessing. And he goes, just guess a pivot point. Now a pivot point is hopefully a number that's near the middle of the range of numbers. There are a number of ways of getting this, but I'm not going to care. I'm going to pick one randomly. So the first thing we do is we pick a pivot point, and then we move the pivot point to the end of the list. So our pivot point is 7, and we're going to move it to the end. So far, so good. Now, for all the numbers in front of the pivot point, we're going to have the items to the right and the items to the left. And we're going to start with the rightmost item and the leftmost item. And what we do is we move the right item left until it points at an item which is more than the pivot point. So we've got the pivot point at the end, that's 7. So 1, that's less than 7. So we move forwards. 6, that's also less than 7. 10 is not less than 7. So we stop that point there. And then we move the left point to the right until it points at an item which is less than 7. And we've got that already. We've got that with 4. So now we have an item on the left which is bigger than the pivot point, an item on the right which is less than the pivot point, and then what we do is we just swap them over. Now that's nice and efficient. We don't have to copy them into any third location. We can just swap them about. And then we rinse and repeat. So step 5, rinse and repeat. We move the left item to the right, the right item to the left, looking for a smaller item. So we'll move that. That's not bigger. That's not bigger. That's not bigger. And that is bigger. Okay, so then we move to the left. And that is bigger. So that's not less. And that is less. So we have a matching pair now, a bigger and a lesser. We swap them over. And then we keep going until the left meets the right, until those 2 pointers meet each other. And at that stage, step 6 is we just swap the pivot point again into the middle. Now at this stage, there are 3 interesting items here. The first one, which is fairly trivial, is that the item which we've moved the pivot point of, the pivot point, has now been moved into its correct position. It will never be needed to move again. But also, all the items on the left are smaller and all the items on the right of the pivot point are bigger. So guess what we do? Yes, we do a quick sort. Yes, we do a quick sort, but we only do it with the items on the left, sans the midpoint, the pivot point. So we pick another pivot point and we divide up. Let's see that in action. So here's our list. I'm using letters this time, not numbers, to show that we can sort anything. And we started off with a pivot point of E. And we're moving the items around. And we've sorted the middle. So now we look at the middle stage. We use a pivot point of A and we do the thing. So now it's sorting from A to E. And then we've done that. So we sort out the middle of that. Then we sort out the other middle. And when that's complete, we're now sorted from A to E. And it then takes the other half, the other large chunk of half, and it does exactly the same thing. So what we're doing is each time when we're sorting less and less and less and less. and then it's complete. So what do you guess the order of this method is? Is it better than merge sort? Is it better than n log n? Is it worse than n log n? Let's have a look. Write it down in your notepad if it's available, and let's see if we can do that. So let's look at the order of quicksort. So we begin with the pivoting process. So this is moving down the array. So let's see, it's moving down the array, and the other one is moving up the array. So it's going to take, it's going to be a for loop followed by another for loop. But because there's one for loop followed by a for loop, we just add them together, not multiply. So if you think about it, no matter how long that array is, if we double the size of the array, it will only take twice as long. If we make it 3 times as longer, it will make it 3 times as long. So it's order of n. The splitting near the middle is recursive. Okay, so I think we have a good idea of how long that's going to take. That's going to take log n, because if we double the size of the system, it's only going to take one extra step. Now, the pivot process is called by the splitting process. So because one is nested inside the other, it means we multiply them together. So that means we end up with n log n. Yes, just like the merge sort. So here we go. So both algorithms happen in the same order of time. Now in practice, people these days typically use quicksort because quicksort doesn't require secondary storage the way that merge sort does. So that's pretty good. So there's an interesting kind of take-home message here, which is Tony Hall might not be the smartest guy in the room, but he can still outdo John von Neumann. Now, of course, people have been looking at sorting since the beginning of computers, and everybody thinks they can do it slightly better. And sometimes there is a particular case. If you know something about the information, you might be able to get away with it. But there are many forms of sorting, and at the moment, no one's ever got better than n log n. We can do a lot worse, but no one's ever got better. So let's stop for a moment and look at sorting in the real world. Let's actually look at practical day-to-day programming sorting. So here we go. Here we've got an array of strings. Okay. So you want to sort that array. What would you do? Well, you could go out and write that algorithm out that I showed you before, or you could just do this. If you have an array of items, you can call arrays.sort, and it will apply quicksort for you, and you're sorted. If you have an array list, you could obviously just convert them to an array and sort the array. But collections, so collections has a way of sorting an array list. So let's just be clear about this. One method to sort arrays, array sort, and that does ints, doubles, floats, characters, those things. And one method to sort lists of objects, and that's collections.sort. And they sort classes, strings, stuff like that. So you just have to pick which one depending upon which data structure you're using. But wait, you're asking, how do I reverse the sort? Supposing I don't want to go from small to big or A to Z, I want to go from Z to A. How do I do that? Well, to do that in Java, you must implement a comparable interface. Now, all a sorting algorithm needs to know is, if I'm looking at this other one, how big is the first one? Is this bigger than me? That's all you need to know. And if the answer to that is yes or no. So here, we need to create a comparable interface. So supposing we had a class book, and the class book has a title, and if we want these books to be sortable, we go implements comparable. Notice it's a generic method, so it uses angle brackets. And we just implement this one method, int compare book. Now, compare to returns one of three numbers. It either compares, it's either less, in which case it returns a negative, or it's more, in which case it returns a positive, or it's the same, so it returns 0. And how sorting algorithms handle similar items like 666, that's very much something the algorithm changes the flavor of the algorithm. But from our point of view, if we want to reverse sort books, we just put a negative on that. So +1 becomes -1, -1 becomes +1, and 0 becomes 0. So here we go. So here is how we would sort an array of books backwards. We would create an array list of books. We would add some books into it, and then we just called sort. And in this case, because the items are sorted by the title, then it will become sorted. Now, sometimes you want to sort on more than one thing. So you want to sort alphabetically on last name and then first name. So you want Dalton Aidan before Dalton Nick. So how would we do that? Well, that's fairly straightforward. What we do is we call the compare method of the object. For example, in this string, we've got one string. So we're going to say in our book, book titles, if they're the same, we're going to sort on the number of pages. So here's a comparison between an object, a string, and a primitive, an integer. So the compare to, that's got to return a number between -1 and +1. And we begin by looking at the title, and we say if the compare to title of this title versus that title, so that's the class, the name of the book, is equal to 0, that's a match. Okay, so now we want to use something else to sort by. In this case, we're returning the number of pages. Now, of course, if one book has 100 pages and another one has 200 pages, then if we subtract 200 from 100, we'll get a negative number. And if we subtract 100 from 200, we'll get a positive number. And if we subtract 100 from 100, we'll get 0. So that's our compare automatically done for us. So all we have to do is say, if the comparison is 0, return subtracting the number of pages. So the names are equivalent. And so now we're going to subtract the number of pages. But here, the names are different because that's false. So we just return which is the bigger book. If you want to sort on the fly, so you're going to sort of sort in a different way, you can actually use this method, which again, the syntax is ugly, but we'll see it in detail in the workshop. So here we say sort, we go round brackets, we begin with the squiggly brackets, and this basically creates an interface on the fly, an anonymous interface that implements the method. So if we want to have a different way of sorting these books, say we want to sort by author and then book title, we can actually just call methods on that thing inside this particular on the fly method. So using comparator, you can sort anything, even if it doesn't know how to sort. So even if your class doesn't have a sort method, you can add a comparator method to do the sorting for you. And in fact, if we're going a little crazy here with a modern version of Java, you can even use a lambda to actually do the sorting. I'm not going to go into lambdas at the moment, but just to let you know, there is actually a shortcut syntax for doing these kind of comparisons. So you're sitting there saying, O of n log n, you don't understand, I need more speed. Well, this is nice because if you implement the comparison mechanism in the modern versions of Java, you can now call parallel sort. So if you imagine back to when we were doing the divide, what we could then do with the divide is actually load each sub array into a different processor, and each different processor could then keep splitting up and doing the work, so that it would all be done in parallel rather than in serial. So in fact, parallel sort does better than n log n a bit. Again, it kind of really depends upon the number of processors you have, but it will give you a slight boost in terms of speed. And if you know your machine has got a large number of CPUs on it, that will actually get you a modicum, a reasonable degree of boost. Not as better as a better algorithm, but it's better than a kick in the teeth. So if you want to understand more about sorting, I would go away and look at the Data Structures and Algorithms book. That's page 103. Downey, the Think Data Structure books, we're looking at chapter 17. And the What Java Collections book, that's page 49. I would definitely go away and have a close look at that. So let's wrap things up. Sorting, it's used everywhere. We've looked at recursion, it's fun and useful. We've looked at bubble sort, merge sort, quick sort. I'd recommend having a look at insertion sort. And we discovered that the best speed we've got at the moment is n log n, with the occasional divide by 8 if you have a parallel machine. The bottom line for this is I don't care if in the long term you remember how these things work. They're very useful if you're trying to understand why your algorithm isn't sorting properly, but you don't really have to understand these algorithms in order to use them. Just use the standard sorting library. So finally, on your notes, I would like to ask you, write down one of the things you've learned today, and if there's anything you didn't understand, or are there any comments, then please make a note about that. Okay, that was the lecture for this week. I hope it was enlightening, and I will see you next week.